In any network, one of the most critical factors is response time, and one of its main enemies is latency. In data center networks, this is not an exception. In fact, the impact of these factors on data center networks is multiplied by the number of users accessing the system. And response time becomes even more critical with applications that are highly sensitive to latency, such as the data streams used in artificial intelligence applications. In fact, in artificial intelligence applications, the time factor is so important that an efficiency metric known as job completion time, or GCT, is used, which measures the total execution time of a task. This metric involves measuring the time elapsed from when the process begins until it ends, taking into account factors such as latency, congestion, and others. In AI, this metric is used to measure efficiency in both training and production processes, whether for large-scale operations or individual requests, as this has a direct impact on the platform's operating cost, user experience, and so on. Therefore, it is important to understand how information flows within a computer from memory to the network interface card. In a traditional server, information is processed in memory. And when it needs to be transferred to another computer, it moves to a buffer known as the kernel, where both the CPU and the operating systems format the information before sending it to the network interface. From there, it's transmitted to the network card of the other computer, which in turn delivers it to its own kernel, which then places it back into memory for processing. Currently, for information processing in artificial intelligence applications, where large volumes of data are handled and latency is critical, this traditional server architecture can be considered a slow process. With the goal of optimizing performance, a high-performance networking technology known as Remote Direct Memory Access, or RDMA, was created, which allows a server to transfer data from its memory to the memory of another server without going through the CPU or the operating system. This technology has a significant impact on improving latency, as information is transferred directly from memory to the network card without the intervention of the CPU or operating system. Upon reaching the network card of the other computer, the information is stored directly in memory for processing. This change in information flow will undoubtedly have a significant impact on the completion time of our tasks, reducing the communication time between servers. However, we must consider another factor. We need to control not only the movement of information within the servers, but also its traffic on the network, in this case, an Ethernet network. For this purpose, a protocol known as RoCE, or Remote Direct Memory Access, RDMA, over Ethernet is used. RoCE, RDMA over Converged Ethernet, is a protocol designed to enable low-latency memory access over Ethernet. To date, we have two versions of the RoCE protocol, which I will explain. RoCE version 1. It was created in 2010 as an add-on to the existing standard known as InfiniBand. RoCE version 1 operates as layer 2 and, since it does not support IP routing, its communication is limited to a single LAN or VLAN. Furthermore, it requires a lossless network using data center bridging, or DCB, for proper operations, as DCB uses a set of enhancements to the Ethernet LAN communication protocol to achieve this objective. Its frame size goes from 1500 bytes for regular frames and up to 900 bytes for jumbo frames. If we analyze the RoCE version 1 data frame, it will look like this. An Ethernet header that contains the layer 2 information associated with the source and destination MAC addresses. EtherType uses the 8915 value to identify the content as a RoCE version 1 packet so that the network can recognize it. Global routing header carries global IDs for source and destination used for layer 2 addressing inherited from InfiniBand. Base transfer header contains opcode that specifies the type or RDMA operations such as read, write, send, ACK, or other control messages. Also includes packet sequence number or PSNs used to track packets and other transport level details for RDMA operations. The payload, the current RDMA data being sent. ICRC or InfiniBand Cycling Redundancy Check, an InfiniBand specific error detection field used for the payload. Frame Check Sequence, FCS, a standard Ethernet cyclic redundancy check or CRC for link layer error detection. However, the need to access different sources of information requires connectivity with external networks or segments beyond the capabilities of a single layer 2 network, which is why RoCE version 2 was developed. RoCE version 2 was created in 2014, enabling layer 3 routing and operating over UDP on IPv4 or IPv6, which has allowed it to interact with larger and more complex networks. Its frame size goes from 4096 bytes up to 9000 bytes. Next, I will describe its structure. As you can see, most of the fields are the same. The main change is that the ether type value is modified to 800 to indicate that the frame is IPv4 or to 86DD to indicate that the frame is IPv6. And then, the most important change. We are going to replace the InfiniBand global routing header with an IP header that contains the IPv4 or IPv6 information of the frame, as well as the protocol, which has the value of 17 to indicate that the frame is UDP. Then, a UDP header is included with the source and destination ports, where the destination port is 4781, which has been established as the standard port for RoCE version 2. And in this way, we can reach more networks beyond our borders, pursuing our goal of optimizing job completion time. To achieve this, we can implement some quality of service functionalities over RoCE, but we will cover that in the next videos. I hope you enjoyed this video. See you in the next one.